Welcome to the Explainer. You know, mastering the art and science of polymer extrusion is honestly a lot like perfecting a high-tech culinary recipe. Think about it. You've got your raw ingredients, heavy-duty mixing equipment, exact temperature profiles you have to hit, and finally the precise shaping of the end product. Today, we're going to completely break down the exact engineering pipeline required to master this process.
Which brings us to our core question for this explainer. How do we actually take raw, formless plastic and engineer it into perfectly precise high-strength products? It's not just about melting plastic and pushing it through a hole. Oh no, it requires a deep, fundamental understanding of material science, thermodynamics, and fluid mechanics.
So, here is our roadmap for today. First, material selection. Second, equipment classification. Third, perimeter optimization. Fourth, we'll tackle the extruder's screw problem. And finally, die calculations.
All right, part 1, material selection, choosing our polymers.
So why use polymers in the first place? Well, they offer some absolutely fantastic physical advantages. For starters, they're incredibly lightweight, usually sitting between 0.8 and 2.2 grams per cubic centimeter. They boast super low thermal and electrical conductivity, excellent chemical resistance, and they require relatively low processing temperatures, typically between 250 and 400 degrees Celsius. Plus, they're just really easy to modify with additives to bump up their strength or flexibility. When you frame these properties against traditional materials, the differences are stark. For example, the thermal conductivity of a polymer is essentially 3 times lower than typical metals, and its electrical resistance is astronomically higher. By selecting a polymer for an extrusion project, we're actively leveraging these exact baselines to engineer products that are lighter, highly corrosion-resistant, and honestly, just far more energy efficient to manufacture. Moving right along to part 2, equipment classification. Let's look at the actual machines. The primary workhorses of this industry are single-screw and twin-screw extruders. Single-screw machines are your standard, reliable, everyday tools. They are fantastic for basic shaping and just continuously pumping out simple profiles. However, when we're dealing with complex composite materials that require really intense blending, we have to step up to twin-screw extruders. These can be parallel or conical, and the screws can rotate in the same direction or opposite directions. This gives engineers vastly superior mixing capabilities. Peeking inside one of these machines, we can map out the critical zones. First, you have the hopper, where the raw polymer enters the system. It drops straight down into the barrel. Inside that barrel is the massive screw itself, which is driven by the motor system in the back. As that screw turns, it physically forces, melts, and pumps the polymer forward towards the die at the very front of the machine. Part 3, parameter optimization. Let's see how this works for manufacturing composite rebar. To truly optimize these machines, let's look at a real-world case study. This operation happens in 3 distinct chronological steps. First, bundles of e-glass fibers are completely saturated in a bath of liquid epoxy mixed with a very specific amount of curing agent. Second, these soaked fibers are forcefully pulled through a cylindrical shaping die to lock in their dimensions. And finally, they pass through a long thermal heating tube for rapid curing. Now, let's map those exact steps onto a factory schematic. On the incoming side, you see the individual bundles of raw fiber being fed into the line. They travel right down into that resin bath to get thoroughly coated. Next, they are pulled up and into the sizing die right in the middle. Finally, they enter the large curing chamber before being pulled by the mechanical traction system and cut to length. Just to ground this theory in reality for a second, here are actual photos from a production line. On one side is the mechanical feeding and pulling system managing the raw glass threads. On the other, you've got the massive 12-meter-long thermal heating tube. The absolutely crucial point here is balancing your variables. If you pull the material too fast, say faster than 1 meter per minute, it simply won't cure fully in the middle. If your temperature in that tube is too high, the epoxy can actually burn, but too low, and the rebar comes out soft and basically useless. To find the absolute perfect recipe, engineers rely on a level 2 orthogonal experimental matrix. They meticulously test different combinations of 3 main variables: the percentage of curing agent, the pulling speed, and the curing temperature. By testing the lower levels against the upper levels, they can mathematically pinpoint the exact manufacturing sweet spot that results in the maximum ultimate tensile stress for the final product. All right, part 4, the extruder screw problem. Time to look at the math. Treating extruder calculations like a giant engineering puzzle, our first fundamental metric is the L/D ratio. That's the length divided by the diameter.
Usually, this sits somewhere between 16 and 36. Now, a longer screw provides much better mixing and a more stable polymer melt, but it's also physically weaker, more prone to mechanical stress, and definitely more expensive. It is a constant balancing act. So here is our specific engineering problem for today. A factory manager needs to process low-density polyethylene, or LDP. We have our machine, we know its geometry, but we need to verify through fluid dynamics if this specific screw can actually push enough molten plastic to meet the factory's target production volume. Well, the manufacturer of our extruder has given us a hard physical limit. The absolute maximum rotation speed of this screw is 108 RPM. We literally cannot run it any faster without severely damaging the motor. So all our calculations have to be based around this peak operational speed. We plug that 108 RPM right into our mass flow equations. We know our material is LDPE melting at 210 degrees Celsius, which gives it a specific density of 750 kilograms per cubic meter. By analyzing the drag flow created by the screw's rotation minus the pressure flow pushing backward, the math gives us a triumphant answer. At maximum RPM, this machine can successfully process approximately 280 kilograms of LDPE per hour. Puzzle solved. Finally, Part 5, Extrusion Die Calculations, the very end of the line. To truly understand die physics, we have to understand shear rate. When molten plastic is forcefully pushed through a narrow die, the layers of fluids scrape against the die walls and against each other. Because polymers are non-Newtonian fluids, this shear rate actually changes the fluid's viscosity. Simply put, the harder you push it, the thinner it gets. Mapping out different manufacturing processes reveals exactly why this matters. Notice how, as the shear rate increases, the viscosity curve drops dramatically. If engineers don't calculate the exact operating point on this curve, they have absolutely no idea how the liquid plastic will actually behave when it hits the die. Which brings us to the ultimate calculation: internal die pressure. Engineers take the complex geometry of the die, calculate the volumetric flow rate based on the pulling speed, and determine the exact shear rate. In our example here, at a shear rate of 1875 reciprocal seconds, the polymer has a known viscosity of 182 pascal seconds. We plug all of this into the pressure equation, and we get our final answer. And the result of that formula is a staggering 205 bar. Just to put that into perspective, that is over 2,900 pounds per square inch of pressure building up inside that tiny metal die. This highlights the extreme physical forces required to perfectly shape the plastic at the very end of the line, and exactly why the mechanical design of the tooling must be absolutely flawless to prevent a catastrophic blowout. So let's pull all of this together. We've completely navigated our core objectives today. We know how to strategically select lightweight, resilient plastics. We figured out how to match those materials with the appropriate single or twin screw extrusion equipment. And most importantly, we've walked through the intense math required to calculate basic processing parameters, from optimizing pulling speeds to predicting extreme die pressures. You now hold the blueprint for mastering polymer extrusion. So, what revolutionary composite will you design next? Thanks for watching The Explainer.